For that, we need to practice matrix multiplication, in particular Boolean multiplication of matrices. And there's a couple of rules we need to keep in mind. And what they are is that 0 is false, 1 is true, plus or addition is the OR logical operation, and the multiplication operation is representing the AND logical operation. In other words, 0 or 0 is 0, 0 or 1 is 1, because false or true is true. 1 or 0 is also 1, because true or false is true. 1 or 1 is 1. And 0 and 0, false and false, is false. False and true is false. True and false is false. Oops. False. And true is true. Notice that when we convert this to the plus and times notation, as seen in the green box and the purple box, a lot of these equations make sense to us, except maybe this last one here. 1 plus 1 is definitely not 1 in regular arithmetic, but in Boolean arithmetic or Boolean algebra, 1 plus 1 is 1, because true or true is true. There's no such thing as 2 in this world. You can't be too true. The multiplication rules also seem to work as well, but I just noticed an error here. Let me fix that. Sorry. 1 times 1 is 1. That definitely agrees with our intuition for arithmetic. We're going to take the matrix that we had earlier and we're going to multiply it with itself using the Boolean version of matrix multiplication. So it's going to look very similar to regular matrix multiplication if you're familiar with that, but with a few adjustments. So I'm going to start by circling the first column of the right matrix and the first row of the first matrix. And the way the matrix multiplication is going to work is as follows. We're going to take the first element of that first row and multiply it with the first element of that first column as follows. So 0 times 0. Might help if we set things up by putting our pluses and our times as needed. Next, we have the second element of that first row times the second element in that first column. So it'll be 1 times 0 this time. 1 times 0. Then we have 0, the third element in that circled row, times 0, the third element in that first column. And finally, we have 0 times 0. And what that all amounts to, 0 times 0 plus 1 times 0 plus 0 times 0 plus 0 times 0, we get 0 plus 0 plus 0 plus 0, which is just 0. And since I circled the first row and first column, then that result will go in the first row, first column of the resulting matrix. Next, we do the same thing with the second row of the first matrix and the first column of the second matrix. So 0 times 0 plus 0 times 0 plus 1 times 0 plus 0 times 0. And again, we're going to get 0 plus 0 plus 0 plus 0, which is 0, which gives 0. If we keep proceeding like this, we'll notice that this column, which is all zeros, is being multiplied component by component with each element in this row, which is going to end up giving us another 0. And similarly for that fourth row, first column entry. Then we take the second column and do the same thing with it. We multiply in this way the second column by each of these rows. And what you might notice is that since the first element of this second column is a 1, we would need a 1 to be in the first element of one of the rows in order to get something other than 0. So it turns out that we actually get zeros all the way down here if you show the work bit by bit. Then you do, again, same thing, but with the third column of the second matrix. So third column times each of the rows. And what you'll notice, the only place that there's not a 0 is that second position of the third column of the right matrix. So the only way we're going to pick up something other than 1 is from this first row, which tells us that here in the first row, third column, we're going to have a 1. And then everything else will be a 0. And you can convince yourself of that by doing the full calculations the way I was showing with the first column times the first couple of rows. And then finally, the fourth column of the right matrix only has a 1 in the third position, so the only way we're going to get something other than 0 is from this second row, because it'll be 0 times 0 plus 0 times 0 plus 1 times 1 plus 0 times 0. So that all amounts to a 1 in that second row, fourth column. Everything else will end up being a 0. Now we're going to link this matrix back to the digraph and the relation and interpret what this matrix tells us. We multiplied the matrix with itself and we got this matrix here. But what does this matrix mean in terms of the digraph and in terms of the relation? Going back to the original matrix, what we notice is we only have a 1 in the matrix in the places where we have an edge connecting those two vertices. So we only have a 1 here because we have the edge from A to B. We only have a 1 here because one edge is from B to C. So what does it mean in this matrix we've multiplied out? What this is saying is now there's a 1 only if you have a length 2 path from a vertex to another vertex. In other words, from A to C, we have a path of length 2, and that makes sense because I have the edge from A to B followed by the edge from B to C. So I have a path of length 2 from A to C. Similarly, from B to D, there's a 1 here because I have a length 2 path going from B to D. Notice that to get transitivity, then, we would want to add in just a single edge from A to C, as this is indicating, and a single edge from B to D, as this is indicating. So this matrix gives us the following information. We have a 1 if there is a length 2 path from one vertex to another. Now what happens if we multiply our original matrix one more time by this result? Let's see what we get.